everybody. You know what time it is. It's time for another exciting episode of HL Chemistry Flipped Classroom videos. And I know you're excited as I'm excited to talk about titrations. So let's get going. Just a quick little review before we start talking about this. This is something I'm sure you all know, but we can remember that acids and bases combine in a neutralization reaction to produce water and a salt. And keep in mind, this is a single arrow here. This is a highly favored to the right type reaction. This is a legit chemical reaction that, for the most part, is going to proceed 100% towards products. And there's our salt there, classic table salt. Just another quick example. Again, here's our salt, but acids, bases, and it's a neutralization reaction, as we've discussed in the past. So a titration. What's a titration? What a titration is for is it's a very precise way of measuring stuff, and it's used to determine the concentration of an unknown substance. And there's a variety of titrations, but the most common type is an acid-base titration, and you're using a neutralization reaction in that case. Usually what happens is an acid is added to a base, or vice versa, until the equivalence point. The equivalence point is when moles of acid is equal to moles of base. So basically we're letting the reaction proceed kind of a step at a time till we get to the point where the two have exactly balanced each other out mole ratio wise. That's when the equivalence point is. And titrations are set up in such a way that they'll use an indicator, and this indicator will turn color in a pH range that's appropriate to the titration in question. How that indicator is chosen, that's a story for another day, but for now we're just going to know that we're going to pick an indicator that's going to work for the titration that we want to do. So there is a formula to help you out with titrations. It's a shortcut formula, and this is going to work best in this form, or really it's only going to work for monoprotic acids and bases with a single OH, and we'll kind of see some examples of what I'm talking about. But a pretty straightforward equation: molarity of acid, volume of acid, molarity of base, volume of base. So we can get the information from a problem, from our experiment, or whatever, plug it in there, and we can find typically what we'd be solving for would be one of these molarities. Now, diprotic acids, like an example of a diprotic acid would be H2SO4. So something like that, where we have two hydrogens. This is going to cause things to get a little bit trickier, where this formula is not going to be directly applied, or we can't apply it directly. We're going to have to do some stuff first. We would want to double the concentration of a diprotic acid like H2SO4 before we put it in this formula, or double the concentration of a base with two hydroxides like this. Now, this isn't going to come up very often. 90% of the time, we'll just be able to use this formula in a really straightforward way. And I'll show you some examples of how that works in just a second. Yeah, like right now. Here's a reaction in a titration example. That was literally like a second. I don't know that you need to like jot down all these examples. There's plenty of examples that you can work through, but maybe just kind of watch as I do this. Suppose 10 milliliters of unknown concentration HCl is titrated at the endpoint with 50 milliliters of 0.3 molar NaOH. What is the molarity of the acid? First, it wouldn't hurt to sort of think about the chemical reaction that's taking place here, the classic HCl plus NaOH reaction to yield NaCl and H2O. Think about our equation there. Now, as long as we know what's what here, we should be fine. HCl, of course, is the acid. NaOH is the base. I'm going to plug it into the formula, plug in what we know. The molarity of the acid is what we're solving for, so that's our unknown. Volume of the acid is 10 milliliters. Molarity of the base is 0.3 from the problem, and oh, I see the problem here. I had changed my mind about the values I wanted to use here. Let's just pretend, and isn't this fun when you're a teacher, you can actually just change the problem rather than changing your answer. Let's pretend that said 20. So now that makes sense. 20 milliliters, that's my volume of base. 0.3 is my molarity of base. What is the molarity of the acid? I'm going to go ahead and solve for that. So some pretty simple algebra here, and we get to the molarity of the acid is 0.6. Now, in this particular case, let's stop and think about that a second. Put on our thinking caps or scarves or whatever clothing you might have nearby. If we kind of look back over what's going on here, the fact that the molarity came out to 0.6 should sort of make sense. They're reacting in a 1-to-1 mole ratio here. We were using 10 milliliters of our acid. That required 20 milliliters of our base. So since it took double the base, double the volume of the base to neutralize this acid, that acid must be twice as concentrated as the base. So our volume of base was double, but that was because its concentration was half of what the HCl was. So hopefully that kind of makes sense in terms of the stoichiometry of the situation. If not, I guess you can just hope that the formula works out for you. So let me show you just another couple of examples. Again, I don't know that you need to furiously scribble down all of this information here. There's plenty of examples, but 25 cubic centimeters of unknown molarity CH3COH is titrated with 0.1 molar KOH. And then we've got the endpoint here after 28.9 centimeters of NaOH. Wow, I'm struggling here. I suppose that should be KOH. Or NaOH. You know, whatever, it doesn't matter. Because the mole ratio is 1-to-1 either way. And all that really matters is I've got an acid-base titration going on here, KOH, NaOH. Either one's going to work out the same stoichiometry-wise. We have 25 cubic centimeters of the acid, so that's my volume of my acid. We're going to solve for the molarity of the acid. Concentration of the base is 0.1, so my KOH is 0.1, and my volume of base is 28.5. So we can solve, just do a little bit of algebra there, and that turns out to be 0.116. So let's just look at another situation. 25 cubic centimeters of unknown molarity HCl is being titrated with 0.1 mole per cubic decimeter barium hydroxide. 11.9 cubic centimeters of barium hydroxide is required to reach the endpoint. What is the concentration of the acid? So what's going to be a little bit different here is, first of all, the stoichiometry of the equation. So because this has two hydroxides, when we end up writing out and balancing the equation, the mole ratio is 2-to-1. Essentially, in terms of its basicity or its base nature, this barium hydroxide is sort of doubly concentrated because it generates 2 hydroxides for every 1 barium hydroxide. So that's what I meant on the other slide about what we'd actually want to do if we want to use that little shortcut equation would be to multiply that base by 2, the concentration of the base, I should say, by 2. Then we can put it into the formula and solve as we did before. So again, the concentration of the base here, if we're going to use that formula, has to be doubled due to the fact that it's got 2 OHs. It makes it twice as tough, if you will, to neutralize. If you're not sure about that or how that all works, these problems can also be solved by solution stoichiometry, and we could talk sometime about some other approaches that you could take to solve these problems. But the good news is, I would say about 90% of the time, you're just dealing with a 1-to-1 mole ratio, and you can just apply the formula sort of in a straightforward manner. So, are you guys enjoying this so far? I hope so. You know what I always say, math is a lot of fun. I don't really think that's true. I don't think math is fun. I wouldn't call it fun. I think it's interesting. I do. I really think it's interesting and it's useful. But I don't know if it's fun. Speaking of interesting, do you know in the United Kingdom they would say maths is fun, like in Britain? Now, I'm not sure I'm correct about that, but I think that sounds right. And if I'm wrong, how do you explain this picture I found on the internet? Is it just some weird typo? But yeah, they say maths over there. Kind of interesting. And math is interesting, and math really is fun. I was just kidding earlier, so don't go telling your math teacher that I said math wasn't fun, because it is. Okay, so we're going to transition here to looking at the workbook, or looking at a page from the workbook. This is page 46 in the edition of the workbook that I'm having here. It looks a little something like this, so I hope you have this and you can find it. What I'm going to do is actually kind of use that simulation program that you may or may not have used before to kind of go along and talk you through this page with the simulation. So I'll be going through the same information, the same stuff, just on the simulation. So if you have this, you might find it handy to sort of place it off to the side as I'm talking about this, because you won't be able to see it when I switch to the other window. So we are going to go to the virtual lab here, the acid-base titration, and I think if I can, I'll maybe provide a link to this so that we can you can play around with it if you need to. So we are going to go on to the titration. So what we're going to be looking at is something called titration curves, graphs that form as we track pH changes during the course of a titration. So we are going to be doing a hydrochloric acid and sodium hydroxide titration again. We're going to do a 0.1 molarity HCl to kind of make the math easy. If you're on your toes here, you'll realize that the pH of this hydrochloric acid, given that its molarity is 0.1, it's a strong acid, so the pH of this HCl is just going to be 1 initially. We're going to use a strong base. We're going to use 0.1. We started off with 25 cubic centimeters or milliliters of the acid, and our burette is going to be filled with the sodium hydroxide. We're going to use the phenolphthalein. So notice that phenolphthalein turns color right around pH 8.2, which is going to work well for this titration. And again, it'll be in another lesson we'll learn more about how to pick appropriate. We'll learn how to best pick appropriate indicators. So here we are. Remember, the HCl is in here. Its pH is 1, and the burette is the sodium hydroxide, and we're going to be adding the sodium hydroxide into the HCl during the course of the titration. And we're going to hope that that color change occurs just when moles of HCl is equal to moles of NaOH. So this is the reaction we're performing, and as we add the NaOH, remember, the flask initially is going to contain nothing but HCl. As we add the NaOH, slowly and bit by bit, the HCl is going to be transformed along with the NaOH into our product here. So initially the pH is 1, so we add a bit of the NaOH. The NaOH is coming out of the burette. It's going in there. Notice here's my amount of NaOH that I'm adding. Notice how slowly my pH is creeping upwards. But think about this. Remember, we started off with 0.1 molar HCl in the flask. If I wanted to change this concentration even from 0.1, or rather if I wanted to change the pH from 1 to 2, that would require my concentration to go from 0.1 to 0.01. I have to have a 10-fold change in HCl concentration to actually make that pH go from 1 to 2. So I would need to actually react almost all of the HCl before the pH is going from 1 to 2. That's why this pH is creeping up really slowly here. So I can speed it up a little bit, and still, again, I have to react almost all of the HCl before my pH is even going to be at pH 2, so it's going to creep up nice and slow. And the way it's set up, we should see a color change here pretty soon, right at 25 milliliters. So, I'm going to stop there, leave you in suspense for just a second. So we're almost there. We're almost at 24.68. So if we think about what's going on in the beaker right now, in the flask, I've just about neutralized all of my HCl with my NaOH, and at some point I'm going to add one last drop of NaOH, and all of my reactant here is going to be gone, and it's going to be completely transformed in my product. And at that exact moment, the pH should be exactly 7. But we've talked before, if a solution isn't buffered, it only takes really small amounts of strong acids and bases to cause the pH to shoot up dramatically. So as soon as it's neutral, that very next drop is going to cause my pH to take this big jump. So as we creep up here to 25, my pH approaches 7, and boom, we kind of jumped right past it, because it's only a matter of a couple of drops that causes pH to kind of launch up dramatically. And what I'm going to do is I'm just going to keep adding NaOH for purposes of the graph that I want to look at. I'm going to run out the whole burette. So there, we've ran out 50 milliliters of NaOH. I've emptied the entire burette into my flask. Now my pH is 9.5, or 12.5, I mean. So what this has done is it's graphed pH changes against volume of NaOH added. So here's my volume of NaOH added, and here's my pH as the reaction proceeds. So at first, I'm just barely creeping up pH-wise. It started at pH 1. I'm just barely creeping up, creeping up, creeping up. Eventually it starts to go up a little faster. I hit this point, the equivalence point, at 25 milliliters. So this vertical line in a titration, that's always going to show up at the point when you've exactly reached the equivalence point, where moles of acid equal moles of base. In the case of this titration, the center of this vertical line is at pH 7. So it just takes a couple of extra drops to cause that pH to shoot way up. So notice in this vertical line, volume, my x-axis volume, is changing very little, only by a couple of drops, but my pH is changing dramatically. So it's kind of important to notice. And then as I continue to add base, strong base, my pH just kind of creeps up and up and up more after that. Eventually, if I put enough base in there, the pH would approach the pH of the base itself, which is actually 13. So let me just kind of review this quickly, because it's an important concept. If we look back at the reaction, I started off with 25 milliliters of HCl in the flask. Its concentration was 0.1, and its pH was 1 at that point, because that's the negative log of 0.1. I was adding NaOH. The moles of HCl in the flask were going down, down, down. The pH was creeping up slowly, because the pH is not going to be 2 until the concentration of HCl drops to 0.01. So I'm going to neutralize almost all that HCl before it goes to pH 2. Since the mole ratio is 1 to 1, when I had exactly 25 milliliters of the base, which also had a concentration of 0.1, at that exact moment, in this instance, I had a neutral solution. And if you think about it, all I had was salt water. Salt doesn't affect the pH in HCl when we talked about salt hydrolysis. H2O, that's neutral. So at the exact moment where the moles of HCl equaled moles of NaOH, these things were completely reacted, transformed into product. So at that point, the pH was 7. The very next drop, now what you're looking at is I'm starting to put excess NaOH into the flask. And NaOH is a strong base. It's going to cause the pH to shoot up really fast. And the more NaOH I put in there, the more and more the pH just pretty much becomes the concentration of the NaOH that I'm dumping into the solution. So the pH is going to match the pH of the NaOH itself eventually if I add enough of it. So that's exactly what we see here in the curve. It's right at that point where moles of acid equal moles of base that we see this vertical line. This is characteristic of all titration curves, is a sharp vertical line at the equivalence point, which in this case is 25 milliliters. So if you look, you should see a graph like that in your workbook. It shows you a different graph to the right of it. What's going on in this different graph is, what if instead of putting acid in the flask, we put a strong base in the flask to start? And let's still have the concentration of 0.1. So sodium hydroxide, concentration is 0.1. It's a strong base, so if I take the negative log of that, that would be 1, but that would be the POH. So the pH of the solution that's going to be in the flask is going to start at 13. And then we'll put an acid into the burette this time, so we're kind of doing the opposite. Now, use phenolphthalein again. Now notice, this time, the phenolphthalein is starting off red, because phenolphthalein is red or dark pink in a base, and I've already got a base in the flask, and I'm adding HCl to it. So the same thing is going to happen, just in reverse. Instead of doing the titration from going clear to pink or red, now it's going to go red to clear. And what I'm going to do is just let all this out right around 25. Again, we see the color change except in reverse. And what we're also going to see is a similar graph except in reverse. We started with NaOH in the flask, we were adding acid, pH creeps down, eventually at 25 milliliters again, moles of acid equal moles of base, and as we continue to add acid, the pH would approach the pH of just the HCl itself that we're adding into it. So that's where those two graphs on the top of page 46 are coming from. These two guys right here. And all this stuff in here is basically talking about what I've just been talking about. So now what we're going to look at is what happens when we add a strong base to a weak acid. See what differences we notice in the curve when that happens. So this time we're going to titrate the weak acid, CH3COOH, with a strong base, NaOH. It's going to be a neutralization reaction. We're going to get a salt and a water. I'm showing the salt in its ionized form here, because that's how it would really look. I really want to emphasize Na as a spectator ion for something we're going to talk about here in a little bit. Just like in the last titration, I'm going to start off with 25 milliliters of 0.1 molar CH3COOH, and I'm going to titrate it with the NaOH. Because the mole ratio is 1 to 1, I'm still going to end up using 25 milliliters of the NaOH to completely react the CH3COOH. The fact that this is a weak acid doesn't affect the stoichiometry. It's still a 1 to 1 ratio. So we're going to notice a couple of differences. If we go back to the beginning again here. So this time what I'm going to do is select the weak acid. Its concentration is going to be 0.1. Now with the HCl, we knew right off the bat that that concentration, or rather the pH of the 0.1 molar acid, was going to be 1. This is not going to be the case with the weak acid. We can't simply take the negative log of this number to get the pH due to the fact that the weak acid's not completely ionized. So the pH that we start at is one difference that hopefully we're going to notice. In the burette, I'm just going to put the strong base NaOH again, and its concentration is going to be 0.1. I am going to go ahead and choose phenolphthalein again here as an indicator. So now notice my pH does not start at the same. It's because I've got a weak acid in here to begin with rather than the strong acid. And I'm just going to run this base out quickly because I want to look at the graph. We should notice right at 25, the color change should still occur right at that same time. Tough to tell. I think there's a little bit of a lag in the way this thing empties out and the pH readings. But as we go on here and we see our titration curve, we notice a few differences. We're starting at a higher pH. This area right here isn't quite as sharp, and we're ending about the same. Another thing I'd ask you to notice is where this line is and where the pHs are. I'll actually go back and show you on the workbook page because it's a little clearer on that one. In our strong acid, strong base titrations, either way we do it, this vertical line, the exact center of it is at pH 7, because when this titration is completely finished, the solution is literally neutral. In the case of this titration, notice that our vertical line is shifted up a little bit with respect to the y-axis, and the center of this vertical line is no longer at pH 7, it's at some a little bit higher pH. So the question we should ask ourselves is, what's causing this? How come the vertical line is shifted up a little bit? The center of it is not pH 7, whereas here the pH is 7, right at the equivalence point. And if we go back and look at these reactions again, in my strong acid, strong base titration, at the exact moment, the exact equivalence point, that is when moles of base equals moles of acid, I had all product. At that moment, the only thing in my Erlenmeyer flask at the equivalence point was H2O and NaCl. NaCl is not a salt that affects the pH, so this mixture is pH 7. However, in the case of the weak acid and weak base titration, at the exact moment when moles of acid equals moles of base. By the way, guys, I find myself pointing to these things with my finger, but I know you can't see that. Anyway, at the exact moment when moles of acid equal moles of base, both of these things were gone. These were completely reacted, and this is what was in my Erlenmeyer flask. Now, what we should know and recall is that the acetate ion is a ion that affects the pH. It is the conjugate base of a weak acid, and therefore it is basic in solution. So at that exact equivalence point, when my flask contained this stuff right here, instead of containing a neutral solution, it contains a solution that's a little bit basic. So this is why at the equivalence point, my solution is more in the basic range of things, right in the center, whereas it was pH 7 at the equivalence point in my strong acid, strong base titration. So I want to look at one more example. This is where we're going to add a strong acid to a weak base. So in the flask, I'm going to put some ammonia, the weak base. Its concentration is going to be 0.1. In the burette, I'm going to put a strong acid. I actually am going to choose a different indicator for this one, and again, in another lesson we'll expand upon why I would choose a different indicator for this one, but suffice to say for now, the phenolphthalein wouldn't really be an effective indicator here. So notice the pH is starting high, because remember this is ammonia, a base in the flask, so my pH is starting high, and we should still see a color change right around 25 milliliters. So I'm going to go ahead and add my strong acid and kind of keep an eye, and somewhere there, yeah, we see the color change. And we're going to see a graph that looks a little bit like this. pH started high due to the presence of the base in the flask at first. It goes up, up, up. At the equivalence point, which again is 25 milliliters, we've been using the same concentrations all along here. We see the characteristic steep line, and then the pH just continues to drop as I'm adding that strong acid to the mixture. So So I know that's some heavy stuff. I know it's some stuff that's difficult to understand, and believe me, you're not the only one if you were a little bit lost at different points during this video. But hopefully this is a good starting point to get us to understand what we need to understand about titrations and titration curves. And if you had some trouble, I'd urge you to go back, watch parts of the video again, look at the information in your workbook, look at the information in your textbook, and see if you can make some sense about what's going on here. You can also go and play around with that titration program I was using yourself and kind of look at what's going on, try to make some sense of the pH changes, play around with it a bit. And there are a couple of other resources that I can link you to, either at the end of the video or on the website. I'll make sure that those links are available. So have fun. Math is fun. Chemistry is fun. And have a good evening. Thank you.